So Michelle is now going to talk about tractography-based parcellation.
All right. So tractography-based parcellations is mainly based on white matter connectivity. So that's probably not the right one. There we go. It stems from the idea of David Venison that areas can be arranged in a well-defined hierarchy on the basis of the pattern of interconnections. So this is a drawing that he did in 1983, connecting like different areas, and you can see that it's extremely complex, but there is overall an organization. And this is fascinating because the value of the input and the output of every area can define the function itself of this area. So if you know very well where the information comes from and where it is going, you can start thinking about organizing a model of how the brain functions. And this idea has been written in 2005 by Mars and Mesulam, who said that nothing defines the function of a neuron more than its connection with other neurons. So, oh gosh, there we go. So why don't we have a parcellation of the monkey brain based on axonal tracing? It's true that this is a gold standard, and you can inject a monkey brain and follow the connections that are emerging and coming from an area according to whether you're using an anterograde or a retrograde tracer. But one key point about like monkey axonal tracing studies is you can only inject patchy areas in the monkey brain to follow their connections. And you have to use different brain to inject separate areas. So even though we have a very valid tool for studying the connection in the monkey brain, we don't have an absolute connectome of the monkey brain using this approach. The other limitation is like the human brain is not a monkey brain, and like every information that we get from a monkey brain neuroanatomy cannot like be directly translated to the human brain. All right, so I spoiled the fun. So today we have diffusion-weighted imaging tractography. All right, it's getting better and better. All right, this is a magnetic resonance imaging approach that allows us to measure the orientation of the diffusion of water molecules in the brain. And the big advantage of that is that like those molecules of water are going to diffuse differently according to the structure and the microstructure of the tissues that you are peering inside the brain. So if we, I didn't touch anything. Okay. All right. If you take on the left a piece of cortex where the constraint of this physical constraint are kind of disorganized, white matter molecules are going to diffuse aleatory, so as you can see in this animation. And the MRI scan is going to record a signal of diffusion-weighted imaging that going to be modelized with a model of tensors that you can see under that look like a sphere because there is no preferential directionality of the diffusion of water inside that voxel. Okay? On the right part instead, so you have like a big zoom image of the white matter. So this is a voxel inside the white matter where axons are packed densely together. Water molecule will not be able to diffuse as freely as in the cortex, and rather is going to diffuse. All right. Going to diffuse along and inside the axons, parallel to the axonal distribution. And the MRI scan is going to record a signal that can be modelized with a tensor model that you can see right under the white matter that looks like an ellipse, which is deformed according to the main orientation of the diffusion of water inside that voxel. This is a simplified explanation on how diffusion-weighted imaging tractography is working. Now, this is a tensor model, and you have more advanced models that can resolve more complex configurations, such as fiber crossing. And for that, you have many other models. If you follow those ellipses, one by one, from voxels to voxel, you will be able to reconstruct major white matter features. So as you can see here, so we have like a few voxels, and if you like, you know, piece it together like that, you can do a 3D reconstruction of big white matter features. But this is very important to keep in mind that those are not fibers, but main orientation of the diffusion of water in every voxels. Okay? So we're not tracking fibers, we're tracking thousands of fibers at the same time. Okay? This gives us the opportunity to track and reconstruct major features of the human brain that actually look like what we can see in the monkey brain. So we're not very different from monkeys, except that we have a bigger brain and extra areas. Here you have an example of the SLF, superior nuclear fasciculus 1, 2, and 3. You can see that we have the equivalent in the human brain. So you have like coronal sections showing you the equivalence between the two species. But doing tractography sometimes also need validations, because if you have very permissive models and you're very obstinate into showing your white matter structure, you may actually succeed. So it's always good to keep in mind that when you're showing new tract and connections, it's important sometimes to also validate it with classical approaches, such as postmortem dissection. So you can see here that the connections are reproducible here in postmortem dissections. Okay? So let's come back to our point, which is trying to divide the brain according to its connectivity as defined by tractography. Okay? So for those of you that don't know tractography that much, I'm going to show you a reconstruction of all the stream tubes that are emerging from the occipital lobe, because we're mainly going to speak about the occipital lobe today. So you can see clearly, so you have the occipital lobe here, that you have many stream tubes that are mimicking like thousands of fibers, as I said, that project towards the frontal lobe and the temporal lobe. So you have like the visual ventral stream here, a little bit of the spinal cord. And even though it looks like very exciting and colorful, it is bounded by limitations. And one key limitation that you can actually observe is if you're looking at the other hemisphere, you can actually see fibers like projecting to the other hemisphere, but when they come across the mid-sagittal section of the corpus callosum, all these stream tubes are intermingled together, and when they're going on the other hemisphere, the topology of what is starting here and finishing there is lost. Okay? So it's very important, if you want to define your areas according to the connectivity, to be sure that the information that you're going to give to your statistical software are not biased by limitation of your method. So in that case, and in the case that I'll show to you, interhemispheric connectivity has been defined as being interhemispheric, but not projecting onto the other hemisphere. By using tractography, many studies have been published in the past years and define like several areas in different parts of the brain that were actually defined by the connectivity with the rest of the brain. So you had the temporoparietal junction, lateral parietal, substantia nigra, cingulate gyrus, lateral premotor, striatum. Broca's areas have been like very well defined, insular cortex that have been divided. The medial prefrontal, which is a classical Johansenberg paper dividing SMA and pre-SMA. The thalamus by Tim Burns, the amygdala, and recently my work on the occipital cortex. One major challenge with this approach is always to find how many parcels you want with your methods. And this has been a limitation in all these studies, for which in my latest study I just found a statistical trick that I'm going to explain to you. So this is how we did it. We recruited like 18 participants, did an acquisition with 60 direction, a B-value of 1500, matrix size of 2 by 2 by 2, plus an imperage T1 imaging of 1 by 1 by 1. Those images were cardiac gated, even though I know that this is not super fashion lately. I want to insist on the fact that cardiac gating is important, and the next slide is going to show you why. So this slide has been the work of Derek Jones. This is a diffusion tensor imaging, RGB maps, acquired at different moment of the cardiac beat. Okay, been synchronized with the cardiac beat, and then he created this animation to show how much the brain might actually move due to the cardiac beat, and this is what you have. So be aware that, like when you do your tractography and when you do your diffusion weighted imaging, if you don't use a cardiac gating, which is going to acquire images synchronized with the cardiac beat, you will have average images that are moving like that. Okay? So we use a two-fiber ball and stick model, which is a classical approach from FSL software. So this is a probabilistic tractography. So we're going to quantify the number of trajectory, emerging, and finishing in different areas as a surrogate for the track, the fiber, the connection strengths. And then we define a matrix of connection and fiber strengths based on a two-region of interest approach. So it's like a small region of interest. You can see here it's like nicely going from one color to the other. Those are like 6 square millimeters region of interest. I'm going to show you in the next slide the example of 2 of these regions. So you have like one in the occipital lobe here, one in the frontal lobe there, and this is a tractography between the two. Okay? And if you look at all those regions, it is actually dispatching on the brain like that. To like a nice rainbow because they cut it from 1 to 5,000 in the frontal lobe. Then to that we added like a couple of regions that were supposed to cover up for the limitations of tractography. So for example, we used like a region of interest for the caudate, the striatum, the thalamus, so 3 separate regions that will code inside the matrix connection to the thalamus or connection to the striatum, to connection to the caudate. And then we also added one region of interest, which was the mid-sagittal section of the corpus callosum as a connection to the other hemisphere, but we didn't use the topology of the other hemisphere in the matrix. As I said to you, because the topology is lost when it's crossing from one hemisphere to the other. So if you do this tractography 2 by 2, correcting for lengths, you might end up with a big matrix. So you'll have your region of interest in the occipital lobe for each column, your region of interest for the rest of the brain, including the occipital lobe, as rows. And here you have your number of streamline or trajectories corrected for the lengths. Okay, you can obtain now this kind of nice tables by using the an option in FSL. Forgot the name of the option, but by that time it was not present, so I had to do it myself. So when you have this matrix, it's actually the option matrix. It's minus matrix when you're launching the tractography. When you have this matrix, you can bring it into a statistical software. So when you want, you can use MATLAB or SPSS to enter it into a statistical analysis, which is called the principal component analysis. Okay? So you have it in MATLAB, in the statistical toolbox. You also have it in SPSS. And then based on that, you can extract your principal components with the first, with the first analysis. So here you have all your components, and they're plotted according to their eigenvalue. Okay? And you have statistical frameworks that have been described by Cattell that can separate what you can consider like a principal components to residual components. It's called the Scree test. So you're trying to find the elbow here, for which we define like a MATLAB tool to do that, and I can send to you if you want. And if you apply that to the occipital lobe, so you can modelize like also this using a power law. If you apply it to the occipital lobe, you will always find a number of cluster of 8.16. We tried also to do that with the Human Connectome project dataset, thinking that having a lower resolution will increase the number of components, and we add exactly the same amount of components with the two datasets. So this is not a matter of resolution, or at least not from 1.25 to 2 millimeters. And so if you have like 8 components, you can run again your principal component analysis by using 8 components as a defined value. So you divide your occipital lobe into 8 clusters. And you can see here the result for an individual subject, okay, because those parcellations are made at the individual level. And here, if you apply it to every participant, you can see the plot of the principal component analysis, all the components according to the eigenvalue. You can see that they all fit the same power law, and they all are around like 8 cluster. And this is the average in the MNI using the maximum percentage, as you've seen with Simon and Matt before. So when you have your cluster, after that you can play around and try to look like what they are connecting. Did the statistic make that job? So we can launch a tractography from every single cluster and identify kind of like the connectome of every cluster. And what's interesting, because here it's probably a little bit hard to read how they differ, you can make a table, try to see what connect what, and you can see that every single of this cluster is showing a different pattern of connectivity with the rest of the brain. Well, this is not very surprising because this is exactly the job that we as a principal component analysis to do. So, but at least it confirmed that it did the job, and it gives us like some information about what are the input and the output of those regions. So the next step really was try to compare this parcellation with other parcellations. We look first at the viability of this region. We look at asymmetry between the right and the left hemisphere, like, just to see whether this was equivalent in the two hemispheres. Found out like the dorsal medial occipital lobe, the regions were actually much more right lateralized. Maybe because it's project onto the dorsal stream, which is supposed to be related to visuospatial attention and dominant in the right hemisphere. And on the right, you have an overlap of every subject. So you have like the probability of finding this area. So the percentage map of every of the cluster, and you can see that it's going pretty high for the core with a descending gradient as you're going further from the center. So those maps are variable from subject to subject. And as I said, we compared that with other parcellation, and I'll focus mainly on the CITO architecture. So you have been having many papers doing tractography-based subdivision, trying to reproduce the division that we have with the CITO architecture. But those are two different things. So if you might think that because areas are different in the CITO architecture, they should have different input and outputs. But that might not hold true for everything. And if you think about it, the striatum got the exact same architecture entirely, but completely different connectivity according to where you go in the striatum. Okay? The motor cortex, you have a different connectivity according to whether you are like in the limb or if you are in the face. The limb are projecting onto the corticospinal tract, while the face is projecting on the corticobulbar. So this is different things. So trying to reproduce CITO architecture using tractography or connectivity-based analysis might not really hold true in terms of neuroanatomy. And this is what we have here. So sometimes you have equivalent for some areas, you know, they look really like the same. For example, take for example HOC4D, which look like really like the area 4 here, and you have like stripes in the brain on the lateral surface, as you have for the C2 architecture. However, if you look at the medial cortex, it looks like you have a division between the peripheral visual field and central visual field, and you have also a division between the ventral and the dorsal visual field. Is it really true, and do we have different connectivity for those areas of the visual cortex? Well, considering the resolution of the tractography, it is actually true that between the peripheral visual field and the central visual field, you have a different input of fibers and systems, such as, for example, you have the parcel and midget fibers. Midget fibers are more likely to project onto the parvocellular, whereas the parcel are more likely to be magnocellular, and they project more likely into the peripheral visual field, while the other one projects more likely into the central visual field. So you have different input in those areas that are supposed to have the same C2 architecture, and this might have changed in our tractography-based subdivision, the division of those areas. Then you have also a division between the dorsal visual field and the ventral visual field. So this is really interesting because those areas might well differ in the way they connected to the dorsal visual stream and the ventral visual stream, which, if you're not familiar about, have a slide here. So the dorsal visual stream is more likely to connect areas that are all about where is this object and the spatial dimension, while the ventral visual stream is more about what is the object that you're looking at and categorization. So if this is really true, well, you know, you should not have the same reaction time if we're presenting object to categorize in your upper visual field on your lower visual field, as well as if you have to do a coordinate task in your upper visual field or your lower visual field, just because it is connected faster to those given systems. And this has been previously demonstrated in a paper of Niebauer in 1998. So that's exactly what they did. They presented like a task of categorization in the upper and the lower visual field, and they found out that actually we are much faster to categorize in our upper visual field than in our ventral lower visual field, which means we are much faster to categorize here than we are here, and just because it is closer to the ventral stream for the categorization. Then they did the same thing with a coordinate task, so a task more spatial, and they found the reverse effect, where you are faster to do categorization tasks in the lower visual fields than you are in the upper visual field. So in here, just because it's closer to the dorsal visual stream. Okay? So it might be a little bit complicated, but it's cross between upper and lower visual field, but overall it works. So you can, the advantage of this method is you can also apply it to like a bigger part of the brain, not worrying about like, you know, how many clusters you're gonna have and the results that you wanna look at. So we applied it to the frontal lobe, for example, and try to see what we had, and we are very pleased to see that we produced like previous results, showing a nice division, for example, between the SMA and the pre-SMA. Then you have like the motor cortex that is like nicely divided. Further area, you have the BA46 that is here. You have division of the frontal pole into a medial and a lateral cluster. So this is a work that is actually submitted. So the take-home message from this will be that, well, you know, you cannot apply this kind of approach on any kind of data set, and indeed the quality of your tractography data set is going to define the quality of your parcellation. Because if you have like bad quality of data set, you're going to have wrong information in your matrix, and you're going to blur your principal component analysis. Then, well, it looks that there is a good correspondence with the functional anatomy of the brain in terms of this division between peripheral visual field and central visual field, or upper and lower visual field. The lateral view was also closer to cytoarchitectonic divisions, and you had those nice areas that were like seems to divide into several consecutive processing of visual information. It seems that there is also a bad correspondence with other divisions of the brain, and this is something that I reported in my paper of 2014 in Cortex. When we're looking at myeloarchitecture and cytoarchitecture, they look sort of close for the occipital cortex, but as we've seen, they do not match tractography-based subdivision. So it's important to keep in mind that those methods are different, complementary, and does not have to show equivalent results. The future directions that we are thinking about, so we want to optimize the processing time because this is obviously very long to do those matrices. We want to optimize also the way we're doing the tractography by integrating Richardson-Lucy spherical deconvolution algorithm, a probabilistic version of it, and we will also wish to release an automatic toolbox for people that want to reproduce this. Thank you very much. If you have any questions.
Thank you very much for your presentation. I was particularly interested in your SVD analysis, but what I did not understand completely is what is inside the matrix. So on the horizontal axis you had the connections from the occipital lobe, and on the vertical axis connections from the left hemisphere.
Yeah.
What is inside the matrix? So on what do you do the SVD analysis? And what I would expect is that you would get regions that are overlapping, but you get clear clusters that are separated in space. So could you give some comments on that?
Well, so inside the matrix, we have the number of trajectories that are reconstructed from one point to the occipital lobe to the entire left hemisphere. Those are corrected for the length. So the further you go, there is a correction because you're losing trajectories as you're going further in the brain. That's a bias of the method. As well as they transform into Z-score because sometimes, a cluster can be misplaced and not very well connected or receive less connections. So I transform everything into Z-scores. And then I run the PCA on that, and the PCA is like categorizing cluster in one or another region.
But why do you get then a parcellation of the columns of your matrix and not of the rows? So why do you not get the parcellation of the left hemisphere instead of the parcellation of the occipital lobe?
Okay, so I didn't do the entire brain, so just because of the time of the processing that was at that time. So I focused on the occipital lobe because there was no paper on the occipital lobe, and I wanted to see whether we'll have equivalent or different parcellation. So now we're going bigger and bigger. I'm buying computers to do the work.
I mean, the operation is completely symmetric. If you transpose the matrix and you do SVD analysis, you would get with the same arguments a parcellation of what is on the vertical.
Well, in that case, you'll parcellate the entire brain based on its connectivity with the occipital lobe, okay. which is an interesting question, but I didn't think about it. I didn't explore that.
Okay, that makes much clearer. Thank you very much.
Thank you.
So I had a question for you, Michel. So divisions of occipital cortex in some ways look similar to what you would see with resting state connectivity, like being able to see dorsal versus ventral. But the cytoarchitectonic boundaries are more, tend to be more in line with things like where the topography of the visual field reverses. So, for example, at the boundary between V1 and V2, you have a reversal. You have the vertical meridian there, and you have a reversal of the topography, and you can see that. You can also see that in resting state. It's not just fMRI that you could see that. And what I'm wondering is if you do you think you could actually, and it's because the parts of say V1 that are given eccentricity in a given polar angle are most connected to that part of V2 and that part of V3 and so on. And I'm wondering if tractography could do something similar where you can actually find the boundaries that match cytoarchitecture based on this more fine-grained connectivity of getting the same part of V1 most connected to the same part of V2 and so on.
Yeah, I think that's a very interesting question. Well, those small connections are hard to track with the actual resolution that we have. So we're mainly using information from long-range connections. And those long-range connections, even in the occipital lobe, are not following classical cytoarchitectural division. So for example, the corpus callosum projects exactly at the boundary between V1 and V2, but not on V1 itself or V2 itself. So it's really like at the border of the cytoarchitecture. So it seems like really like, the connectivity is not following very well the cytoarchitecture, and I have no explanation why for the moment.